Good day. My name is David Ronin Reyes and I am part of Group 4. And for my Lab 4 vlog, part 2, I'll be focusing on half adder and full adder. So our main focus for today is the comparison of um, the half adder and full adder, particularly when both of these adders are created with a 74XX ICs, which you have seen in our Lab 1 vlog, and a comparison to the same adders created using the LOMI that we have created earlier in the part 1 of our Lab 4 vlog. So to get started, I'll be using two applications that I've been using earlier in our part 1 video. So that would be Logism and our Excel file. So let's get started. So as you could see, I have here a um, a truth table for the half adder. So actually, a half adder has two inputs and two outputs, which is the sum S and the carry C. So as you can see, when A and B are both zero, we have uh, a sum of zero and a carry of zero. And as you can see, we have here we have uh, A is equal to 0, B is equal to 1. We have a sum of 1 and a carry of 0. And then an A input of 1, a 0 input for B. We have a sum of 1 and a carry of 0. And when both A and B are 1, we get a sum of 0 and a carry of 1. So upon observation, we could determine that as long as one out of the two outputs has an input of 1, the sum will always be 1. So when comparing the A and B, if both numbers are the same, for example, A and B are both equal to 0 and A and B are both equal to 1, we get a output of 0. So this kind of pattern can also be seen in our XOR truth table. So now moving on to our carry, and as you can see, um, the carry is only 1 if and only if A and B are both 1. So with these truth table, we could come up with equations. So here we could see A prime, B prime, A prime ended with B prime, we could actually get 1. So we put it here. S is equal to A prime B plus A ended with B prime. And as you could see, we also get a 1. So as I said earlier, this equation could be actually simplified to S is equal to A XOR B. Now moving on to our C, we have A only 1, so C is equal to A and B. Now let's move on to our Logism application, and using our 74XX ICs, we could start creating our half adder. And as you could see, we have an XOR here, A XOR B. So we only need A XOR B, and a C is equal to AB, an AND gate as well. And we need an output and another output. So let's label this as A and this one as B. And then we need two outputs. So I'll label this as sum, S for sum, and then this one, C for carry. Now, as we could see, A XOR B, we could just simply put A and then XOR B, and the result will now become our sum. Now let's move on to our C is equal to AB. So let's just simply put B and then A and our C is equal to 0. So let us check if our circuit here is correct. So using the pointer option, we could see A and B 0 and 0 produces a sum and carry of 0. And as long as there is a 1, our sum should be 1. Now let's check our final one. A and B are both 1. Our carry should be 1 and our sum should be 0. And as you could see, this is it. This is how simple we've created our half adder. So let me just move this closer. So that we could save space here. So let's try to create S is equal to A prime B plus AB prime. So as you could see, we need 3 gates for that. So we'll be needing a NOT, and what else do we need? And an OR. So we'll be just actually sharing this outputs. Let me just turn that off first. So let's try to create it using different C, and then let's try X, and then Y. So here we go. Now let's try A prime or X prime plus A prime B. I mean ended with B or Y, and we get this, and we need that output to be ORed with A and then B prime, and our output here should produce this. Label this at sum, and then a carry of AB or XY as well. X, A, and then B. Oh, I made a mistake. B, and then a carry again. Carry. So let's check. So if both X and Y are 0, should be 0. And as long as there is 1, there should be a sum of 1. Correct? Correct. And if both are 1, carry is always 1. So as you can see, using the 74XX ICs, we've actually let me just edit. Let me just input here. Gate, and then gate, and then so I've actually just written this one since this is more preferable. since we've only used two gates for this one. Now let's try creating our half adder with the use of our LOMI. So let me just delete this one since we won't be needing that. So using our LOMI, let's have another input. So this time I'll just put A1 and then another one which is B1. And using our LOMI, um, we don't really have an XOR gate in our LOMI. We only have um, three types of gate in our LOMI: the NOT, the AND, and the OR. And with the use of the LOMI, we should use a, what do you call this, a operator, or as seen is in the table earlier. Wait, I'll just, here, we have this operation mode. And as we could see, the best option we could use is the xy is equal to 0, 0 to get all three types of gates. So in order to do that, we could simply put a ground, which could indicate that x and y are both equal to 0. So this is our x and this is our y. So that means our gate 1 should be an inverter, our gate 2 should be an AND, and our gate 3 should be an OR. So let's go back to our timeline. Let's see our A prime B. So that means we'll actually be needing the negated A. So this is it. And we don't have space for our B. So let me just add one more. Oh, I've actually made a mistake. So let's just add one more again. Then this one. And then it won't work since we've not yet added our xy. So see, this is our A prime, our B prime, and this is our A prime. Now let's add, we'll be needing this first part, which is A prime B. So that's actually an AND gate. So we'll be needing this one, A prime B. So let me just A prime and then B. So this is our A prime B, and then we need it to be ORed. So we could just simply put it to this one, or, and then we need another AND gate, which is for our A and B prime. So let's just do that. A, so let me just delete this, edit it. A and then B prime, and we get that. So we need that result to be ORed, and using the OR gate here, we actually get our output sum. There. And for our carry, unfortunately, we no longer have a space for another AND gate, so we could actually just add another. So using our AB, A, so let me just move this. A, and then B, which is this one, B. We actually have an output here. Oh, I've actually made a mistake. Wait, I'll just put it here, put another LOM there, because we've actually forgotten to put our ground. Wait, I'll just delete that one because um, we know we need more space. Um, we'll be using an AND gate. So we'll be using this one instead because we'll be needing this one, A prime, and I mean A, and then our B. There. So I'm not entirely sure why there is still an error. So let me just delete this one and get another LOMI. So what we'll be needing is AB. So this one A. This is our A. And then our B. And then we should have a carry. I'll just rename this carry. So unfortunately, I think we should refresh our Logism or restart. So I'll just save this, close it, and I'll just open it again. So this actually happens sometimes. So as you could see, we have saved it and it's still an error. So let me just check what's making it an error. A, it's actually correct, I think. A ended with B. I think that's correct. So what's making this error? Our LOMI. Oh, I think yes, our XY. That's our error. So let me just add another A and then a B. Be needing AB. And our carry should be here. And let me just rename this to carry. And let's check using our pointer tool. So as long as A and B are 0, sum and carry should be 0. And as long as there is 1 in our input, our sum should be 1. Correct? Correct. Now if both are 1, there should be a sum of 0 and a carry of 1. So this is actually correct. Now comparing the numbers, number of ICs used, Control C, Control V. for the LOMI, we could actually see that we made use of 3 times LOMI. So when comparing the use of the half adder with the use of 74XX ICs compared to the half adder with the use of LOMI, we could see that the um, the half adder created with the 74XX ICs is more preferable since we've only made use of two ICs and two types, which is XOR and AND gate. So when comparing it to the number of ICs used in our LOMI, we actually made use of LOMI, which is one type and 3 times. So I'll just create a table here in my Excel. So let's just input here for XX. Oh, 7 for XXIC and LOMI. So using that, we actually made use of XOR, and then 1, and then here we actually made use of 3 LOMI in the XY condition. So now we're done with our half adder. So let me just save this. Save. Oh. So now let's move on to our full adder, which is this one. And as you could see, our truth table here has actually 3 inputs, but we have only 2 outputs. So as you could see, A, B, and C in, sum, S, and carry, C out. So in analyzing the truth table, we know that if all outputs are 0, sum and carry are still 0. Now looking at the outputs, as long as um, the 3 inputs has one high frequency input, which is this one, the second row, third row, fourth row, we could say that our sum is 1 and our carry is 0. However, when two there is two high frequency inputs out of the 3, which is our fourth row and our seventh row, we could see that, fourth row, sixth row, and seventh row, we could see that our sum is zeros and our carry is 1. Now, when all of the 3 inputs are 1, our sum and carry should both be 1. So upon analyzing or looking at our table, we can come up with this conclusion or equation. And as seen, S is equal to A prime B prime C plus A prime B C prime plus A B prime C prime plus ABC. So we could actually make it simpler with this by factoring out A prime and A, and when upon uh, simplification, we could come out with S is equal to A, X or B, X or C. So so let me just add a new circuit here. Project, add circuit. Let's name it full adder. Okay. And copy the labels. However, I think we'll run out of space. There. So when comparing the C in our truth table, we could also come up with the equation A prime B C plus A B prime C plus I I meant yeah, that one, A B C prime and A B C. So we could actually simplify it with a C is equal to A prime B plus AB prime plus AB. So we could actually simplify this. Let me just input it here. So C is equal to C A XOR B plus AB. So let me just correct that. Uh, so that we won't so as we see, we could actually use this instead of this one. So let's first start with our uh, full adder with the use of 74XX ICs. So let's first have our inputs A, B, C, in. So we could actually just use XOR gates just to ensure, just to check A, B, XOR C. So our result should be the sum S, and then our C, which is equal to this result. We actually need this result. Ended with, and wait, I just need the end. C in, and then we'll need an AB, A, then a B. Let me just edit this. Should be an A and B, and we'll need a OR gate. So let me just edit this one, OR, which is the result from here and here should produce a output of C. Carry C out. So let us check. Let us check our uh, our circuit. So if all inputs are 0, output should be 0, 0, 0, 1, 1, okay, 0, 1, 0, 1, and then 0, 1, 1 should be 0, 1, correct? 1, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 1, 0, 1, 0, 1, so it's correct. 1, 1, 0, 0, 1, so 1, 1, 0, 0, 1, and finally 1, 1, 1, 1, 1. So as you could see, our adder, we have only made use of 3 gates. So let me just type that here. Gate, and then 1 times AND gate, and then 1 times OR gate. So let me just put it here. So now let's try creating this equation just to make use of the AND or AND NOT gate. But first I'll add another table using 74XX, and then we could actually see that we made it on XOR gate. Hmm. So we made use of um, and then OR. Hmm. So now let's try creating the second equation. So let me just minimize this one and add another one. So let's try rename this with A1, A2, I mean B2. This should be B1, I mean B1, 1, and then C in 1. So to start off, we'll be needing a NOT gate, A, B, and C, A, B, and then C. So let's just add this one, A, B, and then, oh, let me just correct this, B, and then C. So let's first start with our B prime C prime, which is in an AND gate. So we could actually put B prime C prime, B prime C prime, C, we'll only be needing RC, not RC prime. C, we need an OR gate. So we need the results to be ORed with BC. So BC. Mm. And we need this result ended with A prime. So now let's try making our other one. So let's check our, what do you call this? B prime, C prime. So this would be it. C prime, B prime, C prime, plus BC. So we need this ORed. BC. So we'll also need our B and our C again. And its result should be ended with A. And that results should be ORed with one another. So let me just OR this one and then OR this one as well. So that actually is our no, let me just move this. Delete, delete, delete. There. So this actually is our sum. And then using this second one, we would actually be needing another AND gate and 1 2 and another OR gate for our carry. Now let's start with our A prime B, A prime or B, and then A AB, A, then B prime. So we'll be actually needing also our AB here. So let's just get this one. This is our A and then our B. Now we'll have that we'll have this in outputs. Wait, I'll just put it here and then this one here. So we'll also need another AND gate for this one. And this time it's for RC. Let me just put our C all the way here. And the result should be ORed with AB, which is this one. So let's just put it here, have it facing north, and name it carry out. So now let's check if this is correct. If all output inputs are 0, outputs should be both 0. As long as there is a 1, sum should be 1. Now let's check if there are two inputs, which is this one. Carry should be 1, and then this one, and then this one. Correct as well. And lastly, our three ones. So this is actually correct. However, using the second equation for both to avoid our XOR gate, we've actually made use of one NOT gate and then three AND gates, 1, 2, 3, and 2 OR gates. So actually, we could prefer the first equation or our more simpler equation here. Now let's try with the use of using LOMI. So let's just do. So I've actually edited my Excel file. So as you could see, uh, equation 1 here and equation 1 here um, made use of one NOT gate, three AND gates, and two OR gates. However, equation 2 here and here made use of one XOR gate, one AND gate, and one OR gate. Now using our LOMI this time, let's use our LOMI. Let's add another input. This time I'll name it A2, B2, B2, and then C into. Move this downwards. So as you could see, with these three inputs, we'll be needing our NOTs. let me just put 3 here. So here, let me just move it downwards so that we would have more space. So um, in order to create our full adder in our LOMI, we'll be using our our 00 XY operation, so that we would have a inverter, an AND gate, and an OR gate in one IC. So in order to input X and Y, I'll be using a ground. So let me just place a ground here so that it would be automatically considered as 00. So let me just put it here. Oh, I should put there, 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 and there. Now, we could actually start with our uh, equations. Equation 1 for our sum. So it states that we need our A prime. So A prime. Let me just negate everything or come up with its inverted form, and then this there. Actually get B, and then our C. So we'll be needing B prime C. So B prime, let's just put it all the way here. B prime, and then C, ORed with B C prime. B, and then C prime, and the result is ended with A. So let me just ended with A prime. So we'll be needing another end, which is here. Result. So we actually have this first part. We'll need our A, B prime, C prime plus BC. However, we've already used all end uh, our end gates. So let me add more. So we'll be needing three AND gates. Or I mean, three AND gates in our LOMI. So we could actually add 3 more. Now, let us make use of Or let us create our B prime C prime. Just delete this B prime, which is this one. B prime C prime. Oh, I actually made a mistake here. So let me just delete this and this and this. So this is our B prime and then C prime. Now for this to work, let us first connect it all with our X or our operation. Now we have the result here and it should be ORed with BC. So let me just put it here. And then we need ABC here, B, and then AC, just here. C, there. Now we need this result to be A, ended with A. So let me just put it here at the end. And then we need our A, just this one. So we have this here result. Now we'll need a OR gate for our sum. So let me just use this OR gate. Sum, and then the result should be, oh, made a mistake here. Let's try to avoid that passing through our circuit. And we've actually created sum. Now let's move on to our equation 1 in our carry. So we will be needing our A prime B. So we'll be needing AND gates again. So we could actually put 3 more AND gates, or I think we'll be needing 4. I mean 4 LOMIs. So we'll be needing, as observed, we'll be needing a, what do you call this? 1, 2, 3, 4 AND gates. However, we could actually just create 3 using the X and Y 1, 0 operation. So I'll just add a power for, so for that's our 1. And then for our 0, we could add this 1. Now we have all gates in AND form. So we could actually do that here. Wait, so I'll just edit this one, our sum, so that we could save as much as possible. delete, 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 delete. So we've actually deleted this part, which is A, uh, then B prime C prime plus BC. So we'll just need one AND gate for that. So let me just delete first this one. Delete, 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 delete. So that we could actually save our or limit our use of circuits. So for this one, I'll be using the AND gate. So that means 1 and 0. So I'll need the power here. 1, 1 and 0. Now all of these function as an AND gate. So let's first start with our B prime C prime. So as we could see, this is actually, what is this actually? Let me just delete this one, this one. Let me check first. So let's check our A prime, which we have here, our B prime, and our C prime. Now let's check our B prime C, which is this one, B prime C plus B plus B, plus B, which is and C prime. So this is actually correct. Now the result should be here. So what is this? B, A. So this is our result. So actually that's correct. Now let's create this one AND gate. B prime C prime. B prime. And then our, oh, this is actually C prime. Let me just edit. Delete. So we'll be needing our B prime, which is this one, B prime, and then our C prime. So where is our A prime actually connected? So I think this should be A prime, not A. So let me just edit that there. A prime, B C prime, C prime. So we have this, and then we need another LOMI. We're not entirely sure if we'll be needing that yet. So let me just put this here. Then we'll need a BC. So B and then C. The result should be here, and we should get it ended again. Wait, let me just delete this. Ended here. And then we'll be needing our A, is this one, and our sum should be ORed, which means this one, equation here. So this is our sum. This supposedly should be our delete. So let me just uh, add here our output, rename it sum. So that's what we actually have. Now we could move on to our a prime b plus ab plus ab. So we'll be needing uh, two more. And as you could see, we've actually made use of almost all our LOMIs. So let me just clean this up so that we would have space for our other LOMIs. So what we've actually created here is just our S equation 1. Now let's move on to our C equation 1. So let's first have our LOMI, and I think we'll be needing another end. So let's use this. Let's choose this. So all of this are end. This is for our C. Now let's create our A prime B. So our A prime is this one. A prime. And then our B, which is this one. I think we'll be needing two OR gates. So let's have another LOMI. But this time it should be both high frequency. And then we could add this one, because this is A prime B plus AB, so we need an A. And then we need a B prime, which is this one. B prime. B prime, which is then ORed with this one. So the result is then ended with C. So we'll make use of this. And then our C. The result should have okay, let me just add an output, and then let's rename it as, wait, I'll just put it here. So let me just delete this so that we could actually have it here. There. Let me just relabel this as carry C out. This is actually S. There we go. So now let us analyze our LOMI. And as we count here, we've actually made 1, 2, 3, 4, 5, 6 times LOMI. So let's summarize that. So we've actually made use of 3 times xy and 2 times is equal to 0, 0. 2 times xy is equal to 1, 0. And then 1 times xy is equal to 1, 1. So now, when looking at our full adder, we could see that we've come up with this. Now let's check our truth table. So let me just try. If all outputs are 0, sum and carry should be 0. Now if 0, 0, 1, correct. 0, 1, 0, correct. 0, 1, 1, correct. 1, 0, 0, 1, 0. So 1, 0, 0, 1, 0, correct. 1, 0, 1, 0, 1. 1, 0, 1, 0, 1. And then 1, 1, 0, 0, 1, 1, 0, 0 should produce a 1. Now let's check this one. So there's actually an error here in our carry for the last two equations. So let us check our carry if it is correct. So we could see we have here a prime b. C here is, so let me just check, wait. This one is a prime, and then b. This is b. I think this is our CPAL. So let's check our A. This should be A prime, and then B. This is correct, A prime B. And then the results should be then added to our A B prime. So our A B prime is this one, A, and then this one is B prime. And then the result should be then added to our, ORed to our A prime B. So this is it. Now this result should be then ended with our C. And as you could see, this is our C. And the result, okay, that's where we made a mistake. We forgot to add our AB. So to add that, let's add another uh, So I think we'll not be needing our OR here. Let me just edit this. So instead of using an OR here, I mean, we could make use of um, the xy is equal to 0, 0. So first, let's add, oh, but we'll be needing two ORs there. So let me just put that back. Let me just add another LOMI, which will be A and B. So we could actually just put it here, A. So we'll be needing, wait, I'll just delete this. We need our A and B. So this is our A, and then our B. And the result should be added to this one. After ending this, the result should be added here. Delete. So now let's change. Now let's add this. There. We're actually done, but however, we've made use of one more LOMI in the 004, making it 4. And then make this 7. So as you could see, let's check our equations or our truth table if our inputs and outputs are correct. So let's check our 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 0, 1, 1, 0, 1, 1, 0, 0, 1, 0, 1, 0, 1, 0, 1, 1, 1, 0, 0, 1. So we've actually encountered the error here, and now it's correct. Now let's check our last row, which is all 1, and now it's actually correct. So let me just save this. So upon comparison, so upon comparison, um, with the use of our 74XX gates, we could see that our first equation, we made use of 6 gates here. And when we made use of our second equation, we've actually made use of our 3 gates only. So both of these equations are more preferable, both of the use of 74XX gates or ICs are more preferable than the use of LOMI, which made use of 7 uh, circuits or ICs, integrated circuits. And it made use of 3 types, 4XY, 2XY, and 1XY. So that's it for our full adder. Now let's go back to our half adder. And as we could see here, we've actually created the LOMI with just 3 LOMIs. So we made use of 3 times xy is equal to 0, 0. Now, using the first equation that I've showed you earlier, the one we've actually deleted, we made use of um, one AND gate, one times NOT gate, and one times so once I'll just start creating the equation one again just to show you that I've created it in with just three gates here. So let's have the NOT here, A, then B, and then A prime, B prime, and then we'll be needing AND gate, and then an OR gate. So we'll be needing A prime B. So let's have the A prime B ORed with AB. So let's have A, B prime. The result should be ORed, and it should produce our sum, and then our carry is just simply AB. I mean B, and then our A. Output is our carry here. Carry. And as you could see, we've actually created it with just one NOT gate, one AND gate, and one OR gate. And we could test it out. Oh, so we've made a mistake here. Our sum should be, oh no, we're actually correct. So yeah. So in conclusion, with the half adder and the full adder, uh, we could actually say, upon observation and analysis, that the use of 74XX gates are more preferable over the use of the LOMI, which would actually make us use more ICs instead of using fewer ones. So actually, we've finished our half adder and full adder, and that's all for my video. Thank you for listening. Once again, I am David Rodin Reyes, and this is the comparison of the half adder made using the 74XX ICs and with the use of the LOMI, as well as the comparison between the use of a full adder created with the 74XX IC, and the full adder created with the use of LOMI. So thank you for listening.